Hello and welcome to 8.2 Thermal Energy Transfer, video 1 of 3. So just as when you have a balloon that is filled up with air and you release the opening, the air rushes out, it wants to go from a region of high pressure to low pressure. This is pretty typical for most things in nature. Thermal energy behaves very much the same way. So that's what we're going to be looking at in this section. So the first slide that I like to start off with is always the one including the formulas from the data booklet. So here we have 4 formulas, one with power, which we'll see, one with a maximum wavelength, and intensity. Well, you've seen that third one before, and albedo. In today's video, you are going to be introduced to the first 3. But again, we've already seen I is equal to P over A. All right, so I'm going to just skip ahead here and get to our starting slide. Okay, so in a sense, we are starting with thermal radiation here, but we are actually going to go back to it at the end as well and explore it in a lot more detail. So the 3 methods by which thermal energy can be moved and it can change location is through conduction, convection, and radiation. I'm sure these are 3 things and 3 methods that you've learned about even back in grade 7, 8 science. Now, radiation is the only method of transferring thermal energy that doesn't require direct physical contact between the objects. In fact, with radiation, the energy is simply transferred through photons. So photons are particles of light. So if you have a fire burning in a furnace, it is the thermal radiation, it is the energy stored in the photon, the wavelength of light, that gets transferred to your body and heats you up. All right, so we're going to conduction now, and again, we'll come back to radiation. Conduction, when 2 different objects with different temperatures touch, and they have this ability now to transfer thermal energy between them. Okay, so that ability to transfer thermal energy from the hotter object to the colder object is called conduction. All right, so if you remember back in grade 11, we learned about how sound works, and we learned that in a room, wherever you happen to be, there are particles. And if you have a very dense object, those particles are close together. And if you have something like a gas, those particles are further apart. And so this is why we learned that in dense objects, sound actually travels much faster. So sound will travel faster in steel compared to the air. In this case, we're looking at a very similar idea. We're looking at the transfer of energy between particles. And the closer those particles are, the more efficient and faster that transfer of energy will be. And so when you look at the fuchsia colored spheres on your screen, that's what you should think about. These are those particles. Now, on the right side, those particles are very hot. Okay, so you have some other kind of object. And on the left side, they're very cold. Now, as you would have learned in grade 7, 8 science, whether you have an object in solid, liquid, or gas states, they always have moving parts. Okay, so the atoms are always vibrating. And in a solid, even though it might appear as though the atoms are not moving, they are vibrating just within a very limited amount of range. And in a gas, the vibrations are much more. Now, when you raise the temperature of something, the vibrations also increase. So they move more energetically. Okay, so you have these particles near the hot object vibrating, and that energy gets transferred to the line of particles next to it, which gets transferred to the line of particles next to it, and so on and so forth, until this energy gets transferred from the hot object to the colder object. Now, this thermal energy transference will continue to take place until both objects are at the same temperature. Okay, so what we learned about in thermal physics is that we usually associate temperature with kinetic energy. And specifically in this case, it's the kinetic energy of the particles. And these particles are going to vibrate in such a way that the energy will transfer from the object with a high temperature to an object with the low temperature. Okay, now why are metals good conductors? Now they're not just good conductors of electricity, they're also good thermal conductors of heat. And the reason for that is because they have a lot of free electrons. So this is why they make good conductors. Now we can actually measure the rate at which heat energy can get transferred across various types of materials. And so on the slide, you'll see here delta Q. So remember, Q represents thermal energy. So that will be measured in joules. So how much energy gets moved over what period of time? Now, what we learned about when we were studying electricity is that if you have a certain wire, so just imagine that this is a wire, we learned that the bigger the cross-sectional area of the wire, the less resistance there would be. And so that means if you increase this area, the delta Q, the amount of energy transferred per unit time, it should increase. And what we also saw was that if you make a wire longer, that increases the electrical resistance. And so this rate of energy flow should therefore be inversely proportional to this distance that the vibration propagation has to travel. Okay, so there's a lot of factors here. Now, there's another factor as well, and that's the temperature difference. So the bigger the temperature difference, the faster that energy is going to travel. So we can come up with this statement. We know that the rate of energy flow per unit time is directly proportional to the area A, to the temperature change delta T, and inversely proportional to the length, well, the distance that the energy has to travel, D. And so when things are proportional, we say that we can set them equal with a constant. And this K is not just any constant, that's called the thermal conductivity constant. We'll see that on the next slide. Okay, example, excuse me. A brick has a thermal conductivity of K equals 0.710 joules per meter per second per degree Celsius, and the dimensions are shown. All right, two heat sources are placed in contact with the ends of the brick as shown. Find the rate at which the heat energy is conducted through the brick. All right, so we already saw how to do this in the previous, slide. So I'm going to go ahead. Hopefully you have the slides in front of you already. If not, just take a quick picture of the slide you're on so you see the problem in front of you. Okay, we're going to switch screens here so we do the solution. Okay, so we are looking for the rate at which heat energy is conducted through. So that means we are looking for, let's do that. All right, so we are looking for delta Q over delta T. So what we just saw. Now, we also just saw the formula for calculating this. Delta Q over delta T is equal to K times A times delta T divided by D. Now, K, thermal conductivity constant, that depends on the material, right? So for example, here we have brick. Glass would have a different ability to allow this heat energy to transmit compared to brick, which would be different compared to, let's say, lead. Okay, so every material will have its own value, which is why here we're given the K value of 0.710 joules per meter per second degrees Celsius. Okay. All right, so we have that now based on the picture. That's what's telling us the delta T, the change in temperature. So we have 100 degrees Celsius on the hot side, and we have 20 degrees Celsius on the cooler side. So that is a difference of 80 degrees Celsius. Now, keep in mind, just like when we were solving problems in thermal physics with specific heat capacity, a change in temperature, that can be expressed in either Kelvin or Celsius. It'll have the same magnitude. So 80 Celsius is the difference in temperature is the same as 80 Kelvin difference in temperature. It is the actual values that will differ, right? The 100 and the 20. It's just something to keep in mind. And the reason I bring that up is we have a unit of Celsius here. And in this particular case, the thermal conductivity constant is also given in Celsius. If it were given in Kelvin, you got to be careful. Just make sure that what you plug in is also in Kelvin. Okay, so just something to always keep in mind. Now, A is the cross-sectional area. So we remind ourselves cross-sectional area means if you take some kind of three-dimensional object and you were to take a knife and just slice it, okay, if you cut it, what shape would you see on the end? So you cut it perpendicular to its edge, of course. What shape would you see? In this case, you would see a rectangle. Okay, so the area of that rectangle is going to be length times width. Okay, so here we have 0.750 meters times 0.500 meters. All right, so let's see what that's equal to. 0.75 times 0.5. So 0.375 meters squared. All right, so we have delta T, we have A, we just need D, and that's also given in the picture. It's 2.5 meters, or rather 2.50 meters. And that's it for this problem. We just have to plug in our values. So 0.710 joules per meter per second per degree Celsius. times A, that's 0.375 square meters, and delta T, where's that? That's 80 degrees Celsius divided by D, which is 2.50 meters. Okay, now because I'm plugging in all my SI units, and again, the Celsius is canceling out with the Celsius, so that's fine. I'm going to be left with the units that I would expect. Again, Q is a measure of energy, so it'll be measured in joules. T is a measure of time, it'll be measured in seconds. So the unit that I would expect for this is joules per second. So we have 0.710 times 0.375 times 80 divided by 2.5. So we get 8.52 joules per second. So this is the rate of energy transfer. Okay, so with that, we bring to a conclusion our analysis of conduction. All right, so let me just pop through the rest of the points on the slide. That's exactly what we just went through. All right, so next we're going to move on to convection. Now, convection we actually were introduced to in section 8.1 in one of the videos. Convection essentially means you have the movement and motion of a fluid. Now, the word fluid can refer to either a liquid or a gas. Okay, so we're going to be looking at both cases here for convection. In fact, there are so many real-world examples of convection that it just makes sense to go through them all. All right. Now, regardless of which method we're using, conduction, convection, or radiation, this section is on thermal energy transfer. So how does heat move? And it is heat that is moving after all. So think back to when you were a kid, okay? If it's winter outside and you've opened the door to the outside, you may have been told, well, don't let the cold inside, so close the door. Well, this is actually a false statement. Cold air is not what moves. It is heat that moves. Okay, so likewise, when you have the fridge door open, okay, you are actually letting the heat from inside of your kitchen go inside of the fridge. So it is always hot air that moves. Cold air is not what's moving. Okay, so heat energy moves. And that is because by definition, it is the high temperature which gives it the kinetic energy. So it's just something to keep in the back of your head. All right. Now, we looked at this back when we were studying wind turbines to understand how the wind is developed to actually power the wind turbines. And the basic idea is this, and you can see it on the slides as well. If you have some kind of heat source under a pocket of air, that pocket of air is going to start getting warmer. And when things get warmer, the molecules move further apart from each other. There's more space in between them, which means the overall density of that air packet is going down. Now, what you've understood from buoyancy is that when things have a lower density, they move higher than things with a higher density. This is why if you pour some oil on top of water, it will sit on top of the water because it has a lower density. This is how it works. So this source of heat from the ground or underneath the air pocket heats up the air. Okay, so that air becomes less dense, it rises, but as it rises, it moves away from the heat source that originally allowed it to become less dense in the first place. So what happens? It starts to cool. It starts to cool, all right, the atoms come closer together, and this pocket of air now falls. And this cycle continues to repeat itself. And this is how you get what's called a convection current. And so that's demonstrated here in the animation. Okay, so the hot air goes up, cools, comes back down. And so in doing so, we get this cycle, which we'll call a convection current. All right. So let's look at, well, this is exactly the slide that we saw in section 8.1, atmospheric convection in winds. Okay, so something that we learned again when studying thermal physics and specific heat capacity was that land and water have different specific heat capacities. Okay, the reason water has such a big heat capacity is the reason why Australia has much warmer and more stable temperatured winters than we do in the northern hemisphere. There is more water in the southern hemisphere. So while the water does take a very long time to heat up, it also takes a long time to release that energy. Now land, having a smaller heat capacity, will heat up very, very quickly. And so you can just imagine you have this hot piece of land, you have a pocket of air just above the land that's heating up. It's becoming less dense and it starts to rise. Now, whatever used to be in that spot at the bottom is no longer there because the air has gone up. And so what happens is it leaves behind a region of low pressure. And so almost as if a vacuum has been created. There's no more of those air particles because they have gone up. And so other air particles from a different region will move in to take its place. Okay, so that's what you have here, okay, the partial vacuum which has been created. Now, where does that air come from? It's coming from air that has been cooled from the sky. Right? So that is the cooling air that's falling. Well, where does that air come from? That's the hot air that originally rose in the first place. Okay, so overall, you get this convection current. All right. Atmospheric convection again, thunderheads. Okay, so a thunderhead is just a large cloud. Okay, so how do we get convection like this? Well, when you have water droplets become heavy enough, you get rain. And that is just a really simple and yet complex version of convection. Okay, let's look at a more, recent example. Nuclear detonation. Okay, so we spent a lot of time studying nuclear physics in 8.1. So if you were to have a runaway effect with the nuclear fission, you get a nuclear bomb. And this is the basic principle behind how the nuclear bombs work, the runaway effect, the uncontrollable effect. So one of the first things that happens is you have this huge rush of energy and you have a mushroom cloud that gets formed. Now, what you would have seen in the TED Ed video is that the most dangerous part after the nuclear detonation is the fallout. Okay, so once this air, hot air, and this energy rushes up, you have the cooling of this energy, the cooling of this dust and debris, and it begins to fall on top of the land. This is when all the radioactive particles begin to sit and when you don't want to be outside. So this is also an example of a convection cycle. Ocean currents. All right, so this is actually a very complicated example of convection currents. In fact, it's not completely understood yet. Scientists are still trying to analyze these systems. But a big theory on how this works is possibly due to varying temperatures of the water and the wind, because this is what we've seen so far. Things tend to move from regions of high temperature and high pressure to low temperature and low pressure. Now an astronomical example. And so when you look at the picture on your slide right now, it looks like a snapshot of the sun, and you've got a really dark spot in the middle. Now, most of you, I'm sure, have already identified that to be a sunspot. Now, a sunspot is not only a region of very high magnetic field activity on the sun, and that's something else, but it's a region where the temperature is slightly cooler than other areas on the sun. So this part of the sun is not actually black, it just appears black because it's cooler than the surrounding regions. Now, depending on what phase of the sun's cycle you're in, you might have something called a solar maximum where you have a lot of sunspots on the surface of the sun, and then you have the magnetic field switch, and all of a sudden this cycle resets and you get a solar minimum. And now what's interesting is when you have more solar or sunspots on the surface of the sun, more cooler regions, there is less heat, there's less thermal energy coming from the sun to the earth. And it was actually in the past, during an ice age, the ice age occurred on Earth due to a region on the sun's cycle that was at a solar maximum, when there were a lot of sunspots on the surface of the sun and not much heat energy was coming towards the Earth. So something interesting to do some research into if you're interested. Now, if we zoom in near the sunspots, you get these violent eruptions on the surface of the sun. Okay, so one example of these violent eruptions are coronal mass ejections, or CMEs. So what role does convection play here? Well, the sun is, after all, a large ball of plasma. Okay, plasma is just ionized gas. It's just gas that has its electrons separated from its constituent parts. So what's going on here is that heat is transferred from the hot interior of the sun to the outer layers. Now, when you have sunspots, there is no convection going to those regions, and this is why they're cooler regions. And like I mentioned before, they're actually regions of very strong magnetic fields. Okay, moving on to the next example, mantle convection. All right, continental drift, something that you certainly studied in geography courses. Okay, so I'm sure that you saw well, based on the map of the Earth, you can clearly see that if you look on the right of the South American plate, it very nicely fits in with the left side of the African plate. A lot of these continents, if you move them in the right direction, it actually fits together like a piece of a nice puzzle. Okay, so on the left here, we've got a picture of Pangaea. So this was millions of years ago when all the continents were together. They were one big landmass. But due to something called Continental Drift, these pieces have moved apart and they're still moving. So the way you see it today, it's not going to stay like this forever. It's still in motion. Now, the reason these continents are moving is due to something called mantle convection. Now, the mantle is the layer between a planet's core and its crust. And so what's going on here is that the solid mantle is slowly creeping by due to convection currents. And scientists believe that it is heat coming from the interior of the Earth to the surface that causes these convection currents. And if you really think about it, it makes a lot of sense. When you have the sun and you have the energy coming from the core of the sun outward toward the surface through convection currents, that energy transfer is much easier because it's moving within a gas. But if you have that energy moving within a solid, it's much more difficult. And so the motion is not going to be as evident, as significant, but it's still going to be there. So still an area of research. Okay, so that is the end of convection. Now, I did say in the beginning that we would be coming back to radiation, and this is where it is. Black body radiation. Okay, so before we talk specifically about what a black body is, we have to understand how different objects have different colors. Okay? Now, if you have a blue object, you know that when you have light coming in towards that object, white light is comprised of all the constituent colors. Now, if you have a blue object, that means it is absorbing every wavelength of light except for that particular wavelength, which is the color of your object. Okay, so in this example on the slide, we have a green object and you have the incoming white light, which is made up of the constituent colors. Now, you may have heard of Roy G. Biv, ROYGBIV. It's just a fake name given to a way for you to remember the colors that make up white light. Okay, so red, orange, yellow, green, blue, indigo, and violet. Okay, so all of these colors are coming in, but green is reflecting. So whatever color the object cannot absorb is the color that you see it to be. So that's pretty interesting. When we were studying optics and light, what you saw is that when light strikes an object, one of three things can happen. Either it's going to reflect, or it's going to transmit, and by transmission, it's going to be refracting. So, well, perhaps you can count that as two things. Either it's going inside or it's reflecting. Okay, so going inside would be absorption, and reflecting is what causes the specific color the object has. And that's true for any object of any color that fits in within the Roy G. Biv classification. Now, what happens if all of those white wavelengths of light get absorbed? If you absorb all of those wavelengths of light, that means no light gets reflected. That means there is no light to go from the object to our eyes. And so the object becomes black. Okay, we can't see it. And likewise, if an object reflects all the wavelengths of light, it becomes white. So this is where we start to introduce the idea of a black body. A black body not only absorbs all wavelengths of light, but then after it heats up, it re-emits all of these wavelengths of light. Now, a perfect black body is an ideal object. It doesn't exist in real life. But just as a perfect spherical planet doesn't exist in real life, it doesn't mean we can't use approximations. And there are a lot of objects that are similar and model a black body curve very, very well. So I'll show you what a black body curve is on this slide. So on this slide, we're looking and introducing a new piece of terminology, incandescence. Okay, so solids can be heated to incandescence, and different temperatures will have different visible radiation. Incandescence just means when you take an object and you heat it up, its color will change. It can be made up of the same material, but if you change its temperature, it'll emit different colors, or rather in this case, it will reflect different colors. Its properties will change. Okay, so the stove is a great example of this. And while maybe the earlier stoves with the coils visible on the top, not the smooth surface, but the old style stoves, were a better example of this, it still works in the modern stoves. Okay, before you turn on the heat, it is a dark blackish gray color, the coils. But once the heat starts moving, once the electricity starts flowing and it's generating heat, it turns into a red color. Okay, an example not so close to home would be stars. Okay, cooler stars are red. Our star is about a yellowish color. Okay, so yellow and some white. Now, if you're thinking, okay, well, white is a constituent, it's made up of all the colors, that's true. So white, if you approximate where white light lies, it's approximately between the green and the yellow wavelengths. It's about in the middle of the frequencies. Okay, so let's just say that our sun is yellow to orange. I think that's a nice middle place. Now, red would be much cooler, and there's very large, cool stars, for example, Betelgeuse, and yes, that is actually the name of a star. And there's much hotter stars that are blue, for example, Rigel. All right. Now, if we heat up a black body, based on what we saw on the previous slide, it should eventually re-emit this radiation. Now, that radiation gets emitted at various intensities at various wavelengths. Now, you know, if the wavelength of light that is emitted or absorbed, in this case this is emitted, the larger the wavelength of light, the lower the energy of the radiation. And the shorter the wavelength of light, the higher the energy, the higher the radiation. So X-rays would have a shorter wavelength than radio waves and infrared. Now I'm just going to plot a few of these black body curves on this graph, and I'll explain what they mean in a moment. Okay, I've got 3 black body curves here. Now, what I want you to really pay attention to is not only where the peaks are, but the fact that some of them have higher Y values or intensity values compared to the others. Okay, so for example, if you look at this pink fuchsia curve, not only is its peak more to the left of both the orange and red curves, but it emits a higher intensity of radiation at every possible wavelength compared to the other 2 colors. Now, orange, notice again, its peak is slightly to the right of the fuchsia curve. Okay, so its peak wavelength, it's the wavelength at which it is emitting the maximum intensity of radiation, is a little bit larger, so lower energy, than that of the pink curve. And not just that, at every possible wavelength, the Y values are lower. So it's emitting less radiation at every possible wavelength compared to the fuchsia curve. And similarly, if you look at the red, its peak is also shifted even more considerably to the right, and all the Y values are considerably lower. And so what this is going to show is that if you have an object that is red, okay, and you have an object that is orange, okay, so the orange object is, oh, it's a bit hotter than the object that is red. And the purple object, or the fuchsia colored object, or violet, whatever you want to call it, this is much hotter than both of these objects, which is why it's emitting radiation at higher intensities and lower wavelengths. Now, the visible part of the electromagnetic spectrum, so you know the electromagnetic spectrum is all of the various types of radiation that exist in our universe. We have things like X-rays, ultraviolet rays, we have visible light, we have radio waves, we have infrared microwaves. There's all sorts of different wavelengths and categories of light. Now, the wavelength for visible light, it sits within that region that you see on the slide. And if you move a little bit to the left of that, you go into the ultraviolet radiation. Now, in between visible and ultraviolet radiation, there's going to be, well, there's some blurred lines here. Okay, so it's not an exact cutoff, but this is the general idea. Okay, you've got visible radiation, you've got ultraviolet radiation with smaller wavelengths, and then to the right of visible radiation, I've got infrared. And technically, if you were to keep going, then you would get your radio waves and etc., your microwaves, all the other wavelengths. Okay. So what I see is that this object right here, this pink object, is emitting mostly in the visible portion of the spectrum, whereas this orange object is emitting mostly in the infrared region of the spectrum. And as for this red object, it might even be in its own category altogether. Okay, so two trends, and this is what's pointed out on the slides. The higher the temperature, the greater the intensity at all wavelengths. This is what I was saying. The y values are always higher than every other y value of the other curves. Next, the higher temperature, the smaller the wavelength of the maximum intensity. Again, smaller wavelength means higher energy. A trend I want you to notice is that whenever you have a higher temperature, it's also smaller wavelength. Okay, so whatever curve is on top, it should also be more to the left, its peak. Okay, and you can see that as you go from left to right. Okay, you've got the pink curve, highest peak, and it's most to the left. Orange curve is next, lower peak, and it's a bit more to the right. And then you've got your red curve, lowest peak, and its peak is even more to the right. So keep those two trends in mind. And there are the location of the peaks. All right. Now there is a mathematical relationship between that maximum intensity, between that maximum wavelength at which the highest intensity of radiation is emitted, and the object's temperature in Kelvin. And that's given by Wiens Displacement Law. This is a formula in your data booklet. It's one of the ones you were introduced to on the very first slide of this video. Okay, so just remember, please, temperature is in Kelvin in this formula. Okay. The sun's surface has a temperature of 4,500 Kelvin. What is the prevalent wavelength of light? Okay, so we're going to go ahead and use Wiens displacement law. So let's go back to our page here. So we know that the surface temperature of the sun, this is an average, of course, 4,500 Kelvin. We have to find the prevalent wavelength. So this is not the only wavelength that the sun is emitting, but this is the predominant wavelength that the sun is emitting. All right, so using Wiens displacement law, we know that lambda max is equal to 2.90 times 10 to the minus 3 divided by T. Again, T has to be in Kelvin. So we're just plugging in what we know. 2.90 times 10 to the minus 3 divided by 4,500 Kelvin. All right, so grab your calculator. 2.90 times 10 to the minus 3 divided by 4,500. So we get 6.44 times 10 to the minus 7 meters. Now with light, we like to express, especially with visible light, we like to express the wavelength in nanometers. Now nano, the prefix nano, if you look it up in your data booklet, it means times 10 to the minus 9. This answer is times 10 to the minus 7. So if I wanted to make it times 10 to the minus 9, that means I need that decimal to move to the left 2 more spaces, right? So that means I got to stick it right here after the 4. So that means this is the same thing as 644 times 10 to the minus 9 meters, which is 644 nanometers. And so this is the wavelength of maximum emission of radiation from the sun. So going back to the slides, okay, so let's take a look at the spectrum of light. Okay, so there's the visible spectrum. You've got your red wavelengths at around 700 nanometers. You've got your violet at around 400 nanometers. We've got 644, so 644 is right about there. So you're dealing with a bit of an orange color. All right, moving on. Two black bodies, X and Y, are at different temperatures. The temperature of body Y is higher than that of body X. Which of the following shows the black body spectra for the two bodies? Please pause the video at this point and resume it after you have learned and determined what the answer is. We will resume shortly. Okay, so hopefully you paused the video there and tried to figure this out for yourself. Okay, so something very important that I outlined 2 slides ago is that whichever curve is above, its peak also has to be more to the left. Now, if you look at these 4 cases, if you look at B, you can see that Y is above, and it's actually not above for every single wavelength. That's already a problem. right? So if it's above at one wavelength, it has to be above for all wavelengths in terms of intensity. Not to mention that its peak is to the right. So this is wrong for two reasons. D, we have X above Y. Again, it's not above for every wavelength. Excuse me. Even if it was above for every wavelength, the higher intensity emission has its peak more to the right, and that just isn't correct. Okay, so that means we're left with either A or C. Okay, we notice that in this case, the curve that is on top is always on top for every single wavelength. And we can see that the peak is always to the left of the one on the bottom. Okay, so all that's left for you to determine is it Y or is it X that's at a higher temperature? Whichever one's at a higher temperature will have the higher curve. And so, based on the question, we're told the temperature of Y is higher than that of X. Therefore, the correct answer is C. If you want, you can always pause the slides again just to see the step-by-step detailed typed explanation there. Okay, we just have a couple more slides to go in this video. Okay, so we're going to cover next something called the Stefan-Boltzmann law. Okay, so the Stefan-Boltzmann law essentially tells us the amount of power that an object will radiate, specifically a black body. When you know its surface area and you know what temperature it's at, we can figure out how much energy per second is being radiated away. Now, sigma is a constant, that's this symbol right here, and it's given by 5.67 times 10 to the minus 8. You'll find that value in your data booklet under the list of fundamental constants. Okay, so again, this shows the relationship between the temperature of a black body and the power. And as you would expect, the higher the temperature, the more power there's going to be. Okay. So let's move on and try an actual problem. Mercury has a radius of 2.50 times 10 to the 6 meters. Its sunny side has a temperature of 400 degrees Celsius or 673 Kelvin, and its shady side is minus 200 degrees Celsius or 73 Kelvin. I just want you to pause there and really let that soak in. Okay, so if you go out at night here and you find that it's cold, imagine being on Mercury. Okay, the difference between the daytime and the nighttime temperature is 600 degrees Celsius. Okay, that would be enough to make you, well, feel extremely uncomfortable. So why would this be the case? So just take a moment to think about that. Why does Mercury have such a huge change in temperature compared to the Earth? If you'd like, pause the video and try to figure it out. Then in a couple moments, we'll discuss why that is. So hopefully you got a chance to think about that when you pause the video. There's a couple reasons why it has such a big temperature difference. The first is that it's the first planet from the sun. Okay? So you have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. So Mercury being the first planet, that means, well, it's going to be getting a lot of heat during the day. So that explains that extreme 400 degrees Celsius. Now, why does it get so cold at night? Well, it's going to be facing away from the sun, but why isn't it holding on to that temperature? And the reason why it's not able to hold on is because there's no atmosphere. And so the atmosphere is what allows that heat gained from the sun during the day to stay. All right, so going back to the problem, treating it like a black body, find its power. Okay, so we're going to go to the screen here and solve this. All right. All right, so we're dealing with Mercury. Let's see, we know its radius, 2.50 times 10 to the 6 meters. We know that the sunny side has a temperature of 400 degrees Celsius or 673 Kelvin. Okay, so this is temperature H, a hot temperature, and the cold temperature is minus 200 degrees Celsius or 73 Kelvin. Treating it like a black body, find its power. Okay. So based on the Stefan-Boltzmann law, I know that power is equal to sigma A T to the 4. And that sigma is a constant, so I'll just list that over here. So it was given on the previous slide, but you can look it up in your formula booklet as well. So sigma is 5.67 times 10 to the minus 8. And that's watts per square meter per Kelvin to the 4. All right. So sticking those values in, so we've got 5.67 times 10 to the minus 8. You're dealing with a planet here, and the planet is in the shape of a sphere. And so spheres have the following surface area, 4 pi r squared. So here's 4 pi. R is right here, 2.50 times 10 to the 6. That's squared. And multiply that by t to the 4. Now, okay, so we have two temperatures. We have 400 and we have minus 200. So which one are we going to use? Well, we're going to take an average. All right, so my suggestion, don't go with the Celsius. Please only use the Kelvin temperatures here. It only makes sense to use an average because we're given the extremes. So T average is equal to TH plus TC divided by 2. So that's 673 plus 73 divided by 2. Grab your calculator. 673 plus 73 divided by 2. So that's 373 Kelvin. That's a good approximation. Okay, so I'm going to multiply that by 373 to the power 4. All right, grabbing your calculator again. 5.67 times 10 to the minus 8 times 4 pi times 2.5 times 10 to the 6 squared times 373 to the power 4. All right, so what do we get? We have 8.62 times 10 to the 16. Now, what is that unit? Well, it's power. Power is either joules per second or watts. So I'll just list watts here. In the last unit, it was really convenient for us to change watts to joules per second. Here, it depends, I guess, on the scenario, but for now, we'll just leave it in watts. Okay, so there's the power. So going back to the slide. So there's the solution typed up. Now, there's a very important point in the bottom FYI red box, and that is that unless an object is at absolute zero, it will always emit some kind of radiation. So remember, absolute zero is the coldest temperature possible in the universe. It is by definition, the lowest temperature that is achievable. And we did express earlier that whether you have a solid, liquid, or gas, it will always be comprised of particles that vibrate. And it is only when the temperature of that object reaches 0 Kelvin that its movement completely ceases and it stops. Okay, the solar constant. This might seem familiar to you once we start doing some calculations here, but I'll let you discover it for yourself. All right, the sun radiates energy at a rate of 3.90 times 10 to the 26 watts. What is the rate at which energy from the sun reaches Earth if our orbital radius is 1.5 times 10 to the 11 meters? Right, so a couple things to remember. Okay, so if the sun is radiating energy away in a spherical shape, the intensity is going to be much higher if you're closer to the sun, and the further away you are from the sun, the less that intensity is going to get, since that energy gets spread over a larger area. So, well, specifically what we're looking at here is intensity. So if we recall, intensity is power per unit area. So there's that formula once again. We were already introduced to it before, but oh, there it is once again. Okay, so going back to the page here, so let's solve this example. Okay, so we are trying to find the rate at which energy from the sun reaches the Earth. So we are looking for the intensity. Now, intensity is power per unit area. So let's see what we're given. We're actually told the power in the question. The sun radiates energy at a rate of 3.90 times 10 to the 26 watts. And the orbital radius r is 1.5 times 10 to the 11 meters. Now, what you already saw on the slide is that the area we're dealing with is that of a sphere because it's a spherical object, the sun. And so 4 pi r squared is the formula. So I, which is P over A, is 3.90 times 10 to the 26 watts divided by 4 pi times 1.5 times 10 to the 11 squared. All right, so grabbing our calculator, let's put it there. 3.9 times 10 to the 26 divided by 4 pi times 1.5 times 10 to the 11 squared. All right, so we have 1379. I really hope that number looks familiar to you. So about 1375 watts per square meter. Okay, so if it helps, I'll write it like this. 1380 watts per square meter. Okay, so hopefully that number looks a bit more familiar to you. Okay, so this is the solar constant, and we saw it in the last section. This is the intensity of radiation from the sun that reaches the Earth. And just for comparative sake, we'll see how that compares to the intensity of radiation reaching Jupiter at the end of this video. Okay, so going back to the slides, okay, so there's the calculation typed up, and that is indeed the solar constant, the amount of power hitting the Earth from the sun. All right, explain why the solar intensity is different for different latitudes. Again, this question should look familiar. We already looked at this in the previous section. Okay, so depending on what latitude you're at, that intensity of the sun, it's still 1380 watts per square meter, but it depends how many square meters that intensity, that power, is getting spread over. So looking at the bottom arrow here, if you're at the equator, that 1380 watts is getting spread over, well, a relatively small area. And if you go a little bit higher in latitude, well, that 1380 watts or joules per second is getting spread over a slightly bigger area. And if you go even higher in latitude, that area gets increased by so much more. So that same energy per second gets spread over a larger area, which is why it's a lot cooler, well, the more you move away from the equator. So this is one big reason, other than the specific heat capacities. All right, and our last slide and problem for this video. Practice. The sun radiates energy at a rate of 3.90 times 10 to the 26 watts. So there's the solar constant. What is the rate at which energy from the sun reaches Jupiter if its orbital radius is 7.8 times 10 to the 11 meters? So this is Jupiter's solar constant. And really this question is just here for you to see what the difference is and compare. So going back to our page here, so we're looking for Jupiter's solar constant. And so we're looking for intensity. Intensity is power per unit area. Okay. So the power that's coming from the sun, that's not changing. It's still 3.9 times 10 to the 26 watts. What is changing is the distance that we are away from the sun. Okay, so the R is changing, and we're given that R value in the problem. So that's 3.90 times 10 to the 26 watts divided by 4 pi R squared. Okay, so my R value is 7.8 times 10 to the 11 meters. That's it. So grab your calculator, 3.9 times 10 to the 26 divided by 4 pi times 7.8 times 10 to the 11 squared. All right, so that's about 51. All right, so that's a lot less than what we had before. 51 watts per square meter compared to 1,380 watts per square meter. And don't forget, Jupiter is the largest planet, so depending on where you are on the planet, that energy will get dispersed and scattered even more. And so this just goes to show mathematically why the planets, the outer planets, so Saturn, Jupiter, Uranus, Neptune, why they're so much colder than the inner planets. All right, so we're going to stop there for today. So that concludes 8.2 Thermal Energy Transfer, video 1 of 3. Stay tuned next time for video 2 of 3.